好，开始录，还是要等一下开始？开始直接开录。
就直接开始录了吧，没差。
Okay, so we better start. So it's 11 a.m. now. So we have a slight change in terms of the lecture schedule. So Professor Satoru Emori from Virginia Tech will present our second lecture. And he's going to talk about pumping iron, revealing counterintuitive mechanisms of magnetization dynamics. And Professor Emori is currently associate professor at Virginia Tech, and before that, he received his PhD degree from Material Science Department at MIT. I believe that we overlap a little bit when we're there. And then he moved to Northeastern University and then Stanford University as postdoc before joining Virginia Tech in 2017. So let's welcome Professor Emori.
Thank you very much for the introduction, Chi-Feng, and also for the invitation. So I'm very honored to be here in front of a huge audience coming from various parts of the world. Now, so before I get started, so I know that there are quite a few of you folks in the audience who are familiar with Mandarin. I actually cannot speak Mandarin, but I was born in Japan originally, so I know how to write my own name in kanji, Chinese characters. And I looked up the other day how my name is said in Mandarin, so apparently it's Johnson Wu. Did I do it more or less correctly? So yeah, I don't know, if you feel like, if you like to come talk to me, that's another name that you could address me. Cool. So I'd also like to get started with a little bit of self-advertisement. So something that probably a lot of you don't know is, well, where is Virginia Tech? So I like to say that Virginia Tech is located in the eastern part of the United States, and I always tell people, oh, we're quite close to Washington, D.C. Well, truth be told, we are located quite a bit inland, so about several hundred kilometers west. So that's about 4 or 5 hours of driving, and that's close according to the American standard. But that also means that we are located in a very, very beautiful area, right by the famous Appalachian Mountains. So more specifically, we've got quite a few different beautiful natural sites near Virginia Tech. For example, hiking trails with striking views, caves, waterfalls, and there are even many, many farms that brew their own beers and such. It's a very nice area. Now, I'd also like to take a moment to acknowledge both my current and past lab members. So in the interest of time, well, actually, there's one thing I want to say about our lab is that folks come from from various parts of the world. So essentially, just about everybody was born in, raised, and educated in different parts of the world. So anywhere from Florida to Nigeria, China, Iran, and so on and so forth. So it's very much multinational internet. It's a very international. Okay. Now, so what I'm going to talk about today, so we do a fair number of different things, but I'm actually going to focus on just one study, sort of in the interest of time, and so that we can kind of have a more leisurely pace, I guess. So to that end, I would like to give a special acknowledgement to Beru's Kurudari, our former postdoc. So he's the one who spearheaded the work that I'm about to share with you today. Now, so our studies are of course possible, are made possible by a whole array of different collaborators spanning different disciplines and institutions. But in the interest of time, I would like to again give a special thanks to the team from the University of Alabama, headed by Drs. Tim and Claudia Neves. So in this presentation, you're going to see a lot of magnetic resonance experimental results, FMR results. Now, while my own lab actually does do quite a bit of FMR measurements on our own, it turns out that the University of Alabama team had a much nicer FMR facility, or multiple capabilities for FMR. So all the FMR measurements that you're going to see in this presentation actually came from the University of Alabama. Great. Now again, just as I said a moment ago, I'm going to focus just on this one particular study, which was published a few years ago, 2020. With that said, we have been around for 7 years, did a fair number of different things, like, looking into the origin of different mechanisms of magnetic damping, spin current transport. But more recently, our attention has shifted somewhat to sort of exploring the relative orbital and spin contributions to magnetization dynamics, as well as spin orbit torques in sort of unique materials, compositionally graded alloys. So again, I'm not going to be talking about either of these newer studies, but if you happen to be interested, well, please come find me later, and I'm happy to chat. All right, cool. Okay, so that was sort of my long-winded introduction. So now we can get serious and talk about pumping iron. I will say, though, that if you came here expecting me to talk about this former governor of California, I think you would be disappointed. Well, you should have known that. I guess steroids have no place in magnetism. So what I'm going to talk about instead is magnetization dynamics, of course. So we're talking about exciting magnetization in some ferromagnetic material, like a thin film of iron. There are many, many different ways to excite magnetization, including microwave magnetic fields, current pulses, optical pulses, and so on and so forth. And here's a quick picture of the simple representation of what we have in mind here. So when you excite the magnetization, you can get it oriented away from some effective magnetic field. And once you turn off the excitation, the magnetization would not only precess, but it would kind of get sucked in towards the effective field. So it relaxes towards the direction of the effective field. So it is really this relaxation process that we're mainly interested in this particular study. There are different kinds of relaxation mechanisms, but we're going to talk exclusively about so-called Gilbert damping. Okay. Great. Here we go. All right, so here's a quick outline of what I'm going to be talking about for the next 50 minutes or so, and I will make sure to pause here and there so that I can catch some questions. You are, of course, welcome to ask questions at any point during this talk, too. All right. So even though this is a magnetic summer school, I figure that we could have a fairly diverse makeup of audience coming from different expertise, different specializations. So I wanted to make sure that we get started on the same page. So to that end, I'm going to talk about the basics of Gilbert damping, why we care about it, and very briefly how we measure it. Right. And then I'll walk you through our experimental study, first starting with the material, the samples that we study, these thin films of epitaxial iron films as model systems, And then, of course, I will show you our experimental results. You'll be seeing a lot of FMR, ferromagnetic resonance results. So by the way, these are measurements that you can do with instruments coming from quantum design. So Randy will be talking about, I think, some of that this afternoon. There's also some electrical transport measurements. So I'll be showing you some of those. So again, those can be measured, of course, with a variety of quantum design instruments as well. Just a little disclaimer though, we were actually too poor to buy quantum design instruments, but in the future we hope to buy some. So incidentally, I think I just also wanted to clarify that not all American academics in this field are rich, unlike what Professor Hirohata said the other day. All right. And finally, I'm going to wrap up this talk by comparing our experimental results with some of the previously published theoretical predictions, calculations, so that we can sort of make sense out of what's going on. And I will say that this one particular experimental finding that we observe is actually quite counterintuitive. All right, so let's get started with the basics. Here's again the simple picture of the dynamics that we're interested in. Basically, the magnetization misoriented from an effective magnetic field, processing about that effective field. So you won't see a whole lot of equations in this presentation, but this is just one of them. So mathematically, this can be represented by this simple cross product, magnetization crossed by the effective field. And we also have that coefficient in front, which Professor Chang talked about, the gyromagnetic ratio. Right, so of course, this is quite a bit analogous to the precession of a spinning toy top about the vertical axis. But now, just like any real toy top would eventually fall down because you've got friction, in all magnetic materials, you have something that's analogous to friction, what we call damping, which tends to relax the magnetization towards the effective field. So the magnetization doesn't fall down like a precessing toy top. Instead, it gets sucked in towards the direction of the effective field. Right, and this process happens rather rapidly, so on the order of nanoseconds, maybe down to picoseconds, depending on the material that you're looking at. Another thing to keep in mind about damping, again, it's universal. It exists in all magnetic materials, and damping is what allows us to magnetize a magnetic material. So if you think about it, if we didn't have any damping at all, your magnetization would just persist forever and ever about the effective field. You would never be able to magnetize anything. So thanks to damping, we can magnetize stuff. Now here's another equation. So this is that same torque equation that I showed you, but now, in addition to this precessional torque, we have another term that represents the damping torque. So this is the famous Landau-Lifshitz-Gilbert equation that probably quite a few of you have seen. And this is essentially a torque equation representing the net torque acting on the magnetization. Now, as far as this talk is concerned, later on you'll be seeing a lot of this Greek letter alpha, and this is what denotes. This is the parameter that quantifies the strength of the damping torque. This is what's called the Gilbert damping parameter. Right, so Gilbert damping parameter alpha, you'll be seeing quite a bit of that throughout this presentation. Okay. Now let's talk about some possible applications here. Turns out there are quite a few sort of emerging applications in which we want to engineer lower Gilbert damping. So the simple reasoning behind that is, well, damping is again something equivalent, something analogous to friction. So it represents dissipative loss. So it stands to reason that by lowering damping, we can then engineer energy-efficient information and signal processing devices based on nanomagnets. So one simple example, a classic example, is the digital magnetic memory, where you, of course, represent the digital bit using the magnetization direction. And you want to be able to switch back and forth in a controllable manner, and preferably in an energy-efficient manner. So the idea here is that by lowering damping, you can get the magnetization to precess away, spiral away from the initial direction, and then spiral in towards the other direction, thereby allowing you to switch the magnetization. Okay. Now there's a little caveat here, a fundamental trade-off, which is that, well, while it's true that if you want to switch the magnetization with better energy efficiency, you want to have lower damping to initiate the spiraling away process. However, on the other hand, well, if you want to switch the magnetization faster, it actually makes sense to have higher damping so that the magnetization would relax much more rapidly towards the other equilibrium direction. Right, so there's a little bit of a trade-off here. So whether you want to have low damping or high damping probably depends on what you're actually looking for in your application. Now, there are other types of applications where, as far as I'm aware, there are really no trade-offs. You just want to have as low damping as possible. And one class of applications that comes to my mind are the applications based on spin waves. So excitation of magnetization, ripples of magnetization propagating through your magnetic medium. So again, the idea is that by lowering damping, you can then, first of all, generate the wiggling dynamics, and then let the dynamics propagate with minimal loss with a lower amount of power input. So again, in this kind of application, you really just want to minimize damping. All right. So hopefully, just over the last couple of minutes, I convinced you that, well, damping is fundamentally important because it's universal. It exists in all magnetic materials. But from the practical point of view, well, damping does matter. It impacts the performance of various device applications. Now, going back to the fundamentals, though, it turns out, especially from the experimental point of view, the actual exact mechanisms of damping and magnetic relaxation in general are not all that well understood. And this is so even in rather seemingly simple magnetic materials like elemental iron. Okay. So we'll revisit the mechanisms a little later, but for now I'd just like to say a little bit about how we can measure this quantity, Gilbert damping. Typically our go-to technique is ferromagnetic resonance, FMR spectroscopy, which you can kind of think of as a variation of, let's say, absorption spectroscopy. Right? So you shine light into a sample and you monitor how much of that light is absorbed or transmitted. The idea is the same here. So instead of using light, you use gigahertz range microwave excitation. And basically the idea is to monitor how much of the incident microwave power is absorbed by the sample. So looking in more detail what's happening inside the sample, with that microwave field, you're forcing the magnetization to oscillate about an effective field, or in this case the applied field direction. And just like anything that oscillates, the magnetization has its own set of resonance conditions. So favorite frequency with favorite set of excitation frequency and the field magnitude at which it wants to process with its maximum cone angle. Right. So when the magnetization is maximally excited, it's at resonance, you would see a peak in the amount of microwave power being absorbed. Right. So this is just conservation of energy. So it's just telling you that there is a measurable amount of microwave energy from the microwave field being transferred into the sample to drive this precession. Right. So you get this nice peak. Now back to damping. So in terms of measuring damping, what we're especially interested in is the width of this resonance response, what we call the FMR line width. Right. So just to be a little more specific here, if you have a material with low damping, you would expect to see a very tall and sharp resonance peak. Whereas if you have a material with high damping, what you would then see is a shorter or much smeared out resonance response. So this FMR line width can be used as a metric for how much damping there is in the material. Now, so the spectrum that I showed you was obtained at one fixed frequency, but we can then repeat this kind of experiment at multiple different frequencies. And if you're lucky, you're going to see this kind of nice linear relationship between the measure line width and the excitation frequency. All right, so now we can finally talk about this dimensionless parameter, the Gilbert damping parameter alpha. So as long as you have this nice linear relationship and you can, well, there are other some technical considerations, but in the simplest ideal case, you can just use the linear slope of this type of data set, this kind of result, to calculate the Gilbert damping parameter alpha. So that slope is proportional to the damping parameter. So just to give you some rough order of magnitude numbers here. So I know that permolate was mentioned in Professor Brown Cheng's talk. So Gilbert damping for that material, the Gilbert damping parameter of permolate is about 0.006, 0.07, thereabouts. But there are many, many other magnetic metals out there, and you actually find a fairly wide range of damping parameters, anything from 10 to the minus 3 to 10 to the minus 1, so spanning at least a couple of orders of magnitude. All right, so I showed you how we can measure damping, and I promised I would talk about the mechanisms. I'll do that with, oh yeah.
You told us now if we have the diameter of the particles small, so we have a sharper peak, no? And if we have a diameter larger, we have, I mean that's FMR line width. And what about the distribution? If I have a material that have a different diameters, I mean distribution of the diameters. So how can I calculate for example, the damping parameter respecting to this different diameters?
Okay, so you're talking about, so you mentioned nanoparticles and maybe like deep nanometer scale structures.
Ranging between, for example, 30 to 50.
30 to 50.
So I have a different distributions of the diameter.
Yeah. Unfortunately, I don't really have a good intuition for these nanoparticles. So what I'm gonna show you here are just all thin films. But with that said, I think my sort of catch-all answer is it depends. So here, I sort of made it sound like this measured FMR line width is related only to Gilbert damping. That is not always true. Like I said in passing, there are other mechanisms of magnetic relaxation that are actually not Gilbert damping. So one example in particular is what's called two-magnon scattering. So this is a case where you might start out with all your magnetic moments in the nanoparticle processing uniformly, all at the same phase. But in general, if there's anything that breaks translational symmetry in the material, so that could be, well, just any kind of defects, possibly even surfaces in your case. You can have all these spinning magnetization, magnetic moments break up into different phases. So they're not processing all uniformly anymore. When that happens, you would also see the FMR line width increasing. But that's not really Gilbert damping in the strictest sense. It's a different kind of relaxation mechanism.
Okay.
Yeah. And something that's maybe a little easier to picture, if you happen to have a magnetic particle, but the property of that particle itself is not uniform. Maybe it consists of different magnetic phases or something, nanoscale phases. Then each of these phases would have a slightly different magnetic resonance condition. And if you're just measuring the entire particle, you're just going to see kind of the sum or kind of a combination of all these resonance responses. So then you would also see broader FMR line widths as well. So that's called inhomogeneous property. So it actually gets very, very complicated. What I'm about to show you today is a very, very simple picture where things happen to behave very nicely, but I'm glad that you brought this up because in reality, things can behave not so nice.
Thank you.
So point about time. With determining the FMR line, would you like? Okay. So yeah, so on the y-axis there, you've got the power absorbed in arbitrary units, right?
Mm-hmm.
So how do you determine the FMR line width when? So my understanding of the theory is that you can make the sort of a phenomenological description that by fitting a Lorentzi into this equation, and it's the line width part of that. But if you are working in a working out the line width and say like a full width half maximum, you're going to get a different reading depending on the lengths, the units. So for example, in power, if you're measuring say decibels absorbbed in a VNA, right? Whereas if you measure it in milliwatts, you could get a different full width half maximum.
So whether you're on a linear scale or log scale.
Yeah. So I guess my question is experimentally, like in a sort of if you're working with a VNA, say, and you're measuring the dBm absorbed, your S12 parameter, what can you trust the fitted Lorentzian line width for the measurement of damping, or does it need to be converted into a milliwatts reading?
Yeah. I feel like somebody might have asked me that question a few months. I wonder. Anyway,
I think that was me.
So it might have been you. Okay.
Yeah.
So I can tell you about our protocol. So we actually don't use a VNA. We actually just use basically a microwave diode, and so you can use either a DC voltmeter. In our case, we use a lock-in amplifier. So what we're measuring is, I believe, power on the linear scale. Right? So it's not really dBm, so it's in milliwatts, should be. So I would think, that just power, so I think that's okay. So now as to your question, I think I'll have to look into the literature, whether, or maybe you have already.
Well, this is the thing I've been looking for months, and most people report it as an arbitrary unit.
Right.
So, or sometimes it's the derivative, if they're doing a lock-in measurement. So it's quite confusing because again, the traditional treatment is that it's a fitted parameter from a Lorentzian rather than say a full width half maximum that you can definitively extract.
It's true, and almost nobody ever actually reports the actual amount of power being absorbed.
Yeah, exactly. So it's a bit. The damping is already confusing enough, and the literature isn't making it easier. Anyway, thank you so much.
My intuition is, I think things are probably okay as long as what you're measuring is it's on a linear scale.
Right, okay, so in general, treat everything in milliwatts is probably the safest.
Probably, but
thanks.
Okay, any other questions? Yeah.
Thanks. From the FMR line width, I wonder, this is actually in the frequency domain, but if we imagine a precision in the time domain, well, how can this FMR result convert to the time domain? Intuitively, how can we understand the value measured?
Right. So let's see. If you're measuring your response in time domain, well, you're going to see typically what you measure is some kind of damped oscillatory response, and the damping parameter, or I would say effective damping parameter. So taking into account all these other relaxation mechanisms, so that would be related, right, to the rate of the decay. So higher the damping, faster the rate of the decay. Aside from, but I guess that's the most important parameter that we're interested in. With that said, though, things don't always agree between those two measurements, as far as I know. And I believe a large part of that is because, well, so let me put it this way. I think one advantage of this technique is that you can see how the line width scales pretty easily as a function of frequency. So kind of the key assumption here is that this Gilbert damping phenomenon is a viscous effect. So what I mean by that is you should see a linear increase in line width as a function of frequency. So that by itself, again, is not a slam dunk guarantee that what we're seeing is Gilbert damping, but it's a good start. I think from what I understand with time result measurements, I think the interpretation gets a little bit trickier. So how things deal with frequency and whatnot.
So I have a question about the previous slide. Maybe like I'm just curious to know where you have shown that this low damping makes device energy efficient.
Mm-hmm.
So what I got, like when this spin has like lower damping, like we can see it in anti-ferromagnetic materials. Like they should have lower damping. So they may be energy efficient. But like like if we need faster switching, then we cannot use anti-ferromagnetic materials. So like in what cases, like from device perspective, when we need this low damping and when we need this high damping?
So I'm not quite as familiar with dynamics, honestly, dynamics and anti-ferromagnets. So I know that there are claims out there that say damping has to be lower in anti-ferromagnets, or at least certain anti-ferromagnets. From the device perspective, yeah, I mean, I personally don't have a hard and fast rule as to, do we want to be on this side versus that side. I don't know. I mean, all I can say is it just really depends.
I mean, I'm just curious to know, is there any possibility to mix both properties, like and device can be faster switching and energy efficient?
Yeah, so as far as I understand, yeah, I think that's a little tricky. So it is possible that by engineering your materials, so for example, well, I'll say this. So damping is not the only factor that determines the energy efficiency of switching. So there could be, let's say, a different factor like spin torque efficiency. How much spin current or how much spin torque can you get out of, can you get per unit current density or per unit current? So if you can make substantial advances on that front, maybe it matters less that you have high damping. And there are also devices out there that actually do not depend so much on damping, or not at all on damping in terms of energy efficiency. So if you're talking about perpendicular magnetic switching by spin orbit torque, damping, as far as I know, does not come into play. So what you're fighting against is really just magnetic anisotropy. So you lower the magnetic anisotropy to make it more energy efficient, but then there's also a trade-off there in that by lowering magnetic anisotropy, your memory becomes less stable. So just about, I think, any memory devices have some kind of trade-off.
Yeah. Thank you.
Can I add up a very brief comment concerning the time domain picture of the FMR? So, I mean, if you are interested, I do have a very good simulation, which I intended to show, but I did not have time. So after dinner, if you want to, interested in that, I could play my simulation there. So it's experimentally hard to, quantify the time domain picture, but it's theoretically very straightforward. Yeah.
In other words, yeah, I think it's, from the computational point of view, it takes a lot more time and work to produce something like this. All right, so I think in the interest of time, I'll just move on. All right, yeah, lots of good questions, I'm glad. So mechanisms. So earlier on, I said how damping is sort of like a magnetic equivalent to friction. So you might then intuitively think that if you have a magnetic material with less disorder and maybe less electronic scattering, so cleaner materials held at lower temperatures, you might have lower damping. Or at least, I think probably most folks would agree this is kind of the intuitive expectation. And this seems to be backed up by a sort of a rather simple picture of what's actually happening inside the magnetic metal as we have FMR, magnetic precession, and so on and so forth. So when you get the magnetization to precess about some axis, what you're doing is you're artificially creating a non-equilibrium transverse component, right, of the magnetization. So in other words, you have some amount of non-equilibrium spin polarized electrons that are polarized along that magnetization direction. then it seems reasonable that more frequently these electrons undergo scattering. There's a non-zero possibility that these spins will get flipped, they will get scattered. And when that happens, you lose some of that transverse component. So this is sort of the intuitive picture that I think many of us would have. So the more electronic scattering there is, higher damping. Right. But it would be nice if we could somehow experimentally confirm or perhaps refute this picture. So that's what we set out to do. All right. So let me then sort of walk you through how we went about designing this experiment. So in particular, we decided to focus on epitaxial crystalline thin films of elemental iron, BCC iron. And by epitaxial, what I mean is, we grew our thin films on top of crystalline substrates whose lattice parameter is rather closely matched to that of BCC iron. So you get a nice crystalline film. And BCC, of course, stands for body-centered cubic. This is the preferential crystal structure of solid ferromagnetic iron. And okay, why did we decide to take this route? Well, there are some advantages. Well, for one thing, it's a seemingly very simple system. You've only got one element, so you don't really have to worry about any kind of effects or artifacts that might come from chemical inhomogeneities, because there's only one element. Right. And from sort of logistical point of view, there are quite a few different substrates out there that are pretty well lattice matched to BCC iron. Right, so that makes our epitaxial thin film growth much more straightforward. And finally, if we have these nice epitaxial films, it makes it more straightforward for us to compare our experimental results with some of the theoretical computational predictions out there. Because by and large, all these computational work is done on nice periodic systems. So a little bit about how we went about making these iron thin films. So we used essentially the standard magnetron sputtering technique in a high vacuum chamber with a sample held at a balmy temperature of 200 degrees Celsius. For the reason that I'm about to tell you, probably the next slide, we went with two types of different crystal substrates, magnesium aluminum oxide, which I'll call MAO, and magnesium oxide. Right? And we then sputter grew our 25 nanometer thick iron films. We did, of course, grow different thicknesses, but in this presentation, I'm going to focus on just this one particular thickness. And finally, to protect the iron film from spontaneous oxidation, we capped it with 2 or 3 nanometers of titanium. Okay, so what about these substrates? Why do we pick them? Well, so it turns out MAO has excellent lattice matching with BCC iron. So their effective lattice parameters are only off by 0.4% or less. So the resulting film that you get is nice. It's coherently strained to the substrate with minimal defects. So it's got good crystallinity. While for the other substrate, MgO, you have a much greater degree of lattice mismatch, so that the resulting film, while I'll show you that it is still epitaxial, it's not quite as nice. So you're going to have defects here and there to accommodate the lattice mismatch between the substrate and the film. So the easiest way to evaluate the crystalline quality of these thin films is to conduct X-ray diffraction. And what we see here is actually quite straightforward. We just see a diffraction